All right, what's up? We are going to do section 5.4, analyzing graphs of polynomial functions. So we need to be able to graph polynomial functions and identify intercepts, maximums, and minimums, as well as identify the turning points. So starting off, polynomial graphs have hills and valleys. The local max or local maximum is like the local top of a hill. So if we have a graph here, nicely drawn, beautiful looking graph, this right here looks like it's at the top of a hill, so that would be considered a local maximum. A local minimum would be like the local bottom of a valley. So in that same graph, the local minimum would be down here, where the graph starts to change directions again. It looks like a little valley. All right, so tips for graphing. Obviously, checking end behavior was something that we did last unit, so that's a good way to be able to tell if your graph looks kind of like this or that, or like my sketch, something like this or that. It kind of gives you a general idea of the general shape, and then you can also tell how many turning points your graph will have. So for example, if we have a fourth degree polynomial, so an example would be f of x equals 6x to the fourth plus, and then you can have whatever else you want behind it, but as long as 4 is my highest exponent, that means that there will be 3 turns. So it's going to look something like, there's 1 turn, 2 turns, 3 turns. So count them out again here. So this would be 1 turn, 2 turns, 3 turns. And it always works like that. So for the graph below, estimate the x-intercepts. So let's start there. I'll just make a little list off to the side. The x-intercepts are, well, if you zoom in here as best you can see we're at like, I don't know, negative 2.1. comma 0, that would be the coordinates of that point. Again, it's an estimate, it's not perfect if you're wondering where that number came from. Right here, we could say it's something like negative 1.1 comma 0, kind of close, probably not perfect. It looks like we go right through the origin, 0, 0. Here we're a little more than 1, so we'll call that 1.1 comma 0. And then over here, a little more than 2, so we'll call it 2.1 comma 0. So how many turning points do we count? Well, let's see. We have 1, 2, 3, 4 turns, which means if you work this in the opposite order, that would be a 5th degree. Your degree is always 1 more than the number of terms. Oh, put it too high. Let's scoot it down right there. 4 turns, 5th degree. All right, let's try another one here. So we have, here's my x-intercepts list. Looks like we crossed the x-axis here at what would be, so if we're going by 2's here, so this would be negative 2, negative 4. So we'll go negative 4 comma 0. And that's the only time I cross the x-axis, so that is my only x-intercept. There are 2 turns, which would make my lowest degree third. Third degree would be the lowest it could be. All right, so use the graphing calculator to graph. Oh, wow, how convenient. There it is. Look at that. Okay. Use a graphing calculator to calculate the local zeros of the polynomial and any local maximums or local minimums. So while it is conveniently graphed, we do need to open up the graphing calculator app and graph that out quickly. So let it load here. Then go to y equals. Again, if you have anything typed up there, just hit clear before you go ahead and start typing in your new function. So now we're going to go x to the third. Don't forget to hit that little right arrow to bring it back down out of your exponent. Minus 5x to the second. Again, hit the right arrow to bring it down. Plus 4x plus 3. Once you have it typed in completely, just go ahead and hit graph. So we need to calculate the zeros. So we talked about this briefly in, I believe it was the last video, but if you hit the second button and then along the top row, you'll see a button that says trace, and in the top left corner says calculate. So that's the button we want. And here you can calculate any minimum, maximum, any zero, or really any value that you want. So let's go ahead and just review quickly how to find one of the zeros, and I'll let you find the other. So we'll hit enter. And it says left bound, and if you can't see your little dot on your graph, just touch to the left. So I'm going to get close to this point. It looks somewhere like at 1/2-ish, negative 1/2-ish, somewhere in there. So I'm going to go to the left of that, hit enter. Now I'm going to touch to the right of that point and hit enter. And then it says my 0 is at negative 4.6 and 0. So on my sheet here, the x-intercepts are, well, one of them is negative 0.46, comma 0. So what you should do then is go second calculate again, and go ahead and calculate the next one. Left bound, enter, touch to the right of it, hit enter, and then it should tell you kind of right above the y equals button. And I guess I can do this one too. I'll leave one for you. So left bound, sure. Right bound, to the right, good. So now you can see right above y equals there. The x-intercept is 1.76, so we'll go ahead and add that one. I'll leave the third one for you then, 1.76, comma 0. And then you do the same thing basically for the local maximum or local minimum. So I'll run through one of those just really quickly. So we'll go back to second calculate. Let's go ahead. There was a maximum there. Left bound, so right up here is my maximum. So I need to go to the left of it, hit enter. I need to go to the right of it, hit enter, and then it puts the dot there. It looks like it is happening at about 3.88 if you round up. So there's one more x-intercept here. So we'll go maximum was at about 3.88. There is a minimum as well. And if you're wondering where the 3.88 comes from, so I don't know why it's so spaced out, but the x value, the x coordinate of that point is right above the y equals button. The y coordinate is all the way, like right underneath the middle of the graph, right above the draw button. I just rounded to 2 decimal places, so 3.88. And because it's a maximum, I just want the height. And you do the same thing for the minimum. So it does also want the number of turns. And it looks like there are 2 turns. And what is the lowest degree it could be? Well, if there's 2 turns, that means the lowest degree is 3, or third degree. All right, a little bit of critical thinking question here. So if you have a 4th degree polynomial and are given 1 imaginary root, what is the maximum number of real roots? So this goes back to the fundamental theorem of algebra. If it's 4th degree, that means you will have 4 answers. You have 4 answers. Okay, so here's how it's going to work. Just a reminder from the last video that if you have 1 imaginary root, so this is just an example, I don't know, let's go 4i. That means that negative 4i also has to be an answer. So there's 2 of your solutions. You need 2 more. So what is the maximum number of real roots? 2. Because the imaginary take up 2 of our possible answers. So sketch a graph of a polynomial function that has 3 roots. One of them is real. So when you're sketching a graph, this comes back to that end behavior that we kind of talked about in the last unit. So our sketch it is, so 3 roots. So 3 answers, that means it's third degree, which means we have 2 terms, 1 less than that. And then it tells you the end behavior. So what this is saying is, as you go to the right, your function's going down. So start somewhere. Yeah, I'll just start here. You go to the right, your function's going down. As you go to the, well, I shouldn't do that. I'm gonna go down here. As you go to the left, your function goes up. So it's going somewhere up here. And the other thing is, so if it's third degree, we already said it has 2 terms. If there is only 1 real root, that means you only cross the x-axis 1 time. But I need 2 turns. So we could do something like this. So there's 1 turn, 2 turns. There's my real solution. The other 2 would be imaginary. I know this is the last one. I'm not really leaving anything for you to do except just kind of fill in a few things up above. But we'll do one more sketch here because there's a lot going on. It kind of combines a couple sections worth of information here. So sketch a graph of a polynomial function that has 2 roots. None of them are real. So starting right there without looking at anything else, I cannot cross the x-axis with my graph if I have no real solutions. So we have 2 roots. None are real. That means that there is 1 turn. Okay, 2 roots. One turn, sorry. 2 roots, 1 turn. None of them are real. Now looking at the end behavior, so as my function goes to the right, so I'm just going to start right here. My graph goes up. As my function goes to the left, my graph still goes up. So again, it's only going to have 1 turn, and I cannot cross the x-axis. So it's like a parabola opening up that is not going to cross the x-axis.